Hello students, I am Rajni Verma and in this video I will continue graphical representation of motion. We are going to learn about a velocity time graph and how to interpret it. We will also learn to calculate distance travelled and acceleration from a velocity time graph. The motion of an object can be either uniform or non-uniform. We will discuss a velocity time graph for an object moving with uniform velocity and also for an object moving with uniform acceleration. A velocity time graph is plotted by taking time along x-axis and velocity along y-axis. Let us consider the motion of an object in different situations where the velocity at regular time intervals is given. Here we have, in the first case, time in seconds, that is 0, 1, 2, 3, etc. and velocity at such times 0, 2, 4 and 6. We have calculated the time intervals here 1 second, 1 second and 1 second. And the change in velocity in each time interval is also calculated. We see here that 2 minus 0, that is 2, 4 minus 2, 2 and 6 minus 4 is again 2. So we see that the change in velocity in each time interval is the same. So we can say that this is a case of uniform acceleration and non-uniform motion because there is a change in velocity, but the change in velocity in equal time intervals is equal. So from definition we can say that the body is moving, the object is moving in accelerated motion and the acceleration is uniform. In the second case, we see here that again the time intervals are same, 1 second each, and the velocity in each time interval is 10 meter per second. So that the change in velocity in all the time intervals is 0. The body travels with a uniform velocity 10 meters per second and hence we can say that the body is moving with a uniform velocity, and since there is no change in velocity, the object has an acceleration equal to 0. So we see that in case of a uniform acceleration, we got a straight line making some angle with x-axis, while in the second case, when the velocity is constant and acceleration is 0, the velocity time graph is a line, straight line parallel to the x-axis. Let us take another example. The time in seconds and velocity in meter per seconds is given here. We calculate time intervals which are 1 second in each of the case. The velocity in meter per second is given and we see that the velocity is not changing uniformly. It is 0, 2, 1 and 3 for the respective times. The change in velocity is calculated now for each time interval and we see that it is also not the same. For the first pair, 2 minus 0 is 2. For the second one, 1 minus 2, that is minus 1. That means the velocity first increases, then decreases, and then again it increases. 3 minus 1 is 2. When we plot the graph, we find that the nature of this graph is like this. It is not a straight line and the motion is also not uniformly accelerated motion. Although it is a case of non-uniform motion, it is not a uniformly accelerated motion. The motion is non-uniform but the acceleration is also non-uniform. Similarly, for other cases, whenever the change in velocity in each time interval is not the same, we find different natures of the graph. The graph may be a curve, a zigzag, a ladder-like structure, anything but a straight line. So we conclude that the velocity time graph for a uniformly accelerated motion will be a straight line making some angle with the x-axis. But in any other case, when the acceleration is not uniform, the graph will have a nature other than a straight line. We can conclude that the velocity time graph for a uniformly accelerated motion is a straight line, but otherwise, in any other case, it has a nature anything other than a straight line. Now let us see how we can calculate acceleration from a velocity time graph. Here we have two graphs. One is for uniformly accelerated motion where acceleration is not equal to 0, and the other one, as we have seen, the velocity versus time graph is a straight line parallel to x-axis. Since the velocity is uniform, there is no change in velocity, the acceleration here will be 0. So there is no need to calculate acceleration for this graph, although later on we will see that the general method is true for both of these. So let us now calculate the acceleration from this graph. Now let us see how we can calculate acceleration from a velocity time graph. We consider a velocity time graph here and we take 2 points, any 2 points P and Q on this graph. Point P represents time equal to t1 and velocity equal to v1. Similarly, point Q represents time t2 and velocity v2. We draw perpendiculars from P and Q on x-axis and also on we draw perpendiculars from P and Q on x-axis. This one is a perpendicular at time t1 and another time t2. Similarly, we draw perpendiculars on y-axis representing points v1 and v2. We also draw PR parallel to x-axis. Now, according to definition, acceleration is equal to change in velocity per unit time, that is time interval, which can be written as change in time. So we can write it as v2 minus v1 upon t2 minus t1. Acceleration A is equal to v2 minus v1 upon t2 minus t1. Also, from definition, the slope of the graph is vertical change upon horizontal change, which we can write as QR upon PR. QR upon PR. But QR upon PR is nothing but QR is equal to V2 minus V1 divided by T2 minus T1, because PR is the same as T2 minus T1. T2 minus T1, which is nothing but acceleration. From equations 1 and 2 we can see that QR upon PR, which is the slope, gives the acceleration. So we can write that slope of a velocity time graph gives the acceleration. Slope is equal to acceleration, and this is equal to V2 minus V1 upon T2 minus T1, which means that we can calculate the acceleration of a uniformly accelerated motion with the help of a velocity time graph by calculating its slope. Recall, we have studied in detail about slope. Slope is nothing but the vertical change upon horizontal change between any two given points. Here we have taken 2 points P and Q, and the slope is QR upon PR. And also from the graph we see that this is equal to V2 minus V1. So the slope is V2 minus V1 upon T2 minus T1, and from definition, acceleration is nothing but change in velocity upon change in time, that is V2 minus V1 upon T2 minus T1. So this is our formula. Slope is equal to acceleration is V2 minus V1 upon T2 minus T1. So slope of a velocity time graph gives us the acceleration. Let us now calculate the distance travelled by an object moving with uniform velocity. Here we have the velocity time graph of such an object, which is a straight line parallel to x-axis. From definition, we know that velocity is equal to distance travelled per unit time, or we say that V is equal to S upon T. V is equal to S upon T, which implies that S is equal to V into T. That is, distance travelled is equal to velocity into time. Now let us consider the graph, and we take any 2 points A and B. We want to know what is the distance travelled when the body moves from point A to B. Let A represent time t1 and velocity v. Similarly, at point B, the time is t2 and the velocity is the same, that is v. Now ABCD is a rectangle, and we may see that the area under this graph, this is a rectangle, the area under the graph or the portion of the graph AB is a rectangle ABCD. So area under graph AB is equal to area ABCD, or area of the rectangle ABCD, and we know that area of a rectangle is equal to length into breadth. So area of rectangle ABCD is equal to AB into AD, or AB into BC, or AD into DC, or any such pair. We have to take the length into breadth. So area of rectangle ABCD is equal to AB into AD, but this is AB is equal to T2 minus t1, sorry, t2 minus t1, and AD is v, or the velocity, the uniform velocity. Therefore, area of rectangle ABCD is t2 minus t1 into v, but this is nothing but the distance travelled. So we can say that this is distance travelled S, or S is equal to area under the graph. So we see that the area under any portion of the graph, or the area under the graph, gives us the distance travelled for that portion of the graph. So when the object travels from point A to point B, the distance travelled by it is given by the area under the graph. This is an important relation. We can easily calculate the area under the graph, and so even without doing further calculation, only by calculating the area under the graph, we can calculate the distance travelled by the object during that portion of the graph. This is for uniform velocity. Now let us see how we can calculate distance travelled for uniform acceleration from a velocity time graph. We consider a velocity time graph OAB, where points A and B are such that point A represents time t1 and velocity v1, while point B represents time t2 and velocity v2. Here again, just like the previous case, when the velocity was uniform, the distance travelled is given by the area under the graph. So when the motion of the object is represented by 2 points A and B for time interval t2 minus t1, let us calculate what is the distance travelled. So the distance travelled, since it is the area under the graph, it will be distance travelled is equal to the area ABCD, which is the area of a trapezium, and this can be broken into two parts, that is area of rectangle AECD plus area of the triangle ABE. We can also calculate the area directly by using the formula for the area of trapezium. Now you may wonder, how is that possible? Because in the previous case, when the velocity was uniform, the area under the graph was a rectangle and the distance travelled was easily calculated by the area of the triangle. It was simply equal to the velocity into time. But here it is not the same case. As the velocity keeps on changing, we cannot say that we can directly multiply velocity and time. It is not a uniform velocity. Now if you remember, the average velocity is calculated as say v2 plus v1 upon 2. And by definition, average velocity is that velocity which makes the object travel the same distance in the same time interval as is travelled by a variable velocity from v1 to v2. So the average velocity will be in the middle of this line segment AB. Let us suppose this is the point which represents the average velocity v. If the object travels with a constant velocity equal to the average velocity v, the graph of its motion will be a line parallel to the x-axis. Let us suppose this is denoted by PQ. Now we see that this is a rectangle and we see two triangles which make opposite angles here, and we can find out that the area of these two triangles is equal, so that the area PQCD is equal to the area ABCD. So the distance travelled by the object with variable velocity or uniformly accelerated motion is the same as the distance travelled by the object if it were to move with a constant velocity equal to the average velocity. So we can calculate the distance travelled by the object by calculating the area under the graph. So in all cases, area under the graph is equal to the distance travelled. So as we see, the distance travelled is equal to area of trapezium ABCD. We can use the formula to calculate the area of trapezium ABCD. The area of trapezium is calculated by the formula half sum of parallel sides multiplied by the distance between them. So this is equal to half sum of parallel sides AD plus BC multiplied by the distance between the parallel sides. This is T2 minus T1, or say this is equal to AE, which can be written as half AD is V1 plus BC is V2 and AE is equal to T2 minus T1. V1 plus V2 upon 2 is the average velocity and T2 minus T1 is the time interval. So this is average velocity multiplied by the time interval. So this formula agrees with the formula for the distance travelled. Distance travelled S is equal to V into T. Here average velocity acts as the velocity and time interval t. So s is equal to v into t, and the distance s here is also equal to average velocity into time interval. Therefore, the area under the graph of a uniformly accelerated motion also is given by area under the graph. S is equal to v into t, where v is the average velocity. Here are the informations obtained from the velocity time graph. Nature of the graph gives the nature of motion. As we have seen, if the graph is a straight line making some angle with x-axis, it is a uniformly accelerated motion. If the graph is parallel to x-axis, it means that it is a uniform motion, the velocity is constant and the acceleration is 0. For any other type of graph, that is, if the nature of the graph is anything but the straight line, it is a motion such that the acceleration is not uniform. The area under the graph gives the distance travelled. The acceleration of two motions can be compared by comparing the slopes. So we have studied both distance time graph and the velocity time graph. In all cases, the nature of the graph and the slope of the graph are very important, while with the help of the velocity time graph, we can calculate one more quantity, that is, area under the graph gives the distance travelled. So that's the end of the video, students. In our next video, we shall learn about the equations of motion and how to derive the equations of motion by the graphical method. Thanks for watching.